Hello to everyone, I'm America Califano, and today I'm going to discuss the microclimate into Ringebu and Heddal stave churches, focusing on whether the European standard EN15757 is a reliable tool to assess the decay probability of Scots pine wooden elements. But first of all, which is the motivation of this study? Well, there is the need of a strong control strategy for the mixed microclimate in Ringebu and Heddal stave churches. As a matter of fact, they are managed with artificial heating in cold months and with no heating in warm months. So there's a mixture of natural and artificial microclimate. Especially when there is the use of heating, it is important to avoid over dryness of wooden building assets and artifacts stored within the churches for ensure their conservation. So it is fundamental to identify possible risky events due to the mixed microclimate management. In this framework, can the European standard be supportive in a mixed microclimate condition? So with these ideas in mind, the talk will be structured as follows. First of all, I will describe you the case studies with their monitoring campaigns, and I will describe the collected data and metadata. Then I will present a strategy to identify the relative humidity variations due to use of heating based on the European standard, focusing on its critical issues. And then I will propose a possible new strategy for a better identification of the relative humidity variations, focusing on differences with the previous strategy and showing you a relation that links relative humidity variations to agromechanical stress. And finally, I will discuss the results and conclude. Concerning the case studies, they are Ringebu and Heddal stave churches. They are located in Norway and are almost completely made of Scots pine wood. During the simple project, they were equipped with 3 data loggers. So each church was equipped with 3 data loggers, and data have been collected since March 2019. Up to now, we have collected data until October 2020. The observed quantities are temperature and relative humidity. And as I've just said, 3 data loggers were positioned in each church. 2 data loggers were positioned indoor, labeled as DL1 and DL2, and the third one was located outdoor and was labeled as DL3. From now on, I will be focusing on 1 year observation, so going from March 2019 to March 2020, but in detail, the year observation comprises 13 months, as suggested by the European standard. Here you can see the temperature relative humidity data collected using the data loggers for the 2 churches. In particular, the top 2 graphs represent the relative humidity. In gray, you can see the outdoor relative humidity, while in blue, the indoor relative humidity for the 2 churches. The black curve is the central moving average, and the red curves are the 70th and 93rd percentiles of the relative humidity computed following the European standard. The 2 bottom graphs on the other end represent the temperature. In green, you can see the outdoor temperature, while in orange, the indoor temperature. And just taking a quick look at the indoor temperature profiles, you can see how the 2 churches are managed with a different use of heating. As a matter of fact, in Ringebu, we can see several peaks of temperature, while in Heddal, we can just observe a plateau of temperature. We own not only data, but even metadata, that is to say, information about the use of the churches. So we have information about the date and time of scheduled events, like services, wedding, funeral, concerts, and we have information like the number of people attending each event. Analyzing metadata, we were able to extrapolate the occurrence of the events and their duration. It is clear that the most frequent events are Sunday services and funerals. Concerning the use of heating, it was clear from the temperature profiles that there's a different kind of heating management for the 2 churches. As a matter of fact, for Ringebu Church, there's a sporadic use of heating. This means that the heating is turned on only in case of events in the period of time that goes from half September to half April, more or less. While in Heddal, there is a continuous heating. So in order to ensure an almost constant temperature of about 5 centigrades, and in case of events, the temperature is further risen for the people's comfort. And the heating is usually turned on from October to May. Here you can see an example of temperature and relative humidity profiles in Ringebu Church during Christmas week 2019. The orange curve is the temperature, while the blue curve is the relative humidity. These bars represent the occurrence of event. Different colors stand for different events. The position of the bars represents the date and time of the beginning of each event, and the thickness represents the duration of each event. So here we have 1 concert and 3 Christmas celebrations. We can see how analyzing the temperature profile, at the end of each event, the temperature starts to decrease. So this means that the heating has been turned on. As a matter of fact, turned off, sorry. As a matter of fact, the heating is turned off at the end of every event. But if we take a look at the temperature profile, or particularly at the relative humidity profile, we can see how the temperature starts to rise several hours before the start of the event. So this means that the heating is turned on many hours before, but with no general rule. It could be interesting and fundamental to evaluate when the heating is turned on in order to understand the impact and the effect of the use of heating on all the wooden objects stored within the church. From now on, I will focus on Ringebu Church, but then finally I will show you results even for Heddal Church. So if we want to have a general idea of the effect of use of heating on relative humidity, we can use the European standard to compute the relative humidity fluctuations and compute the central moving average and the percentiles. Here you can see again in gray the outdoor relative humidity, while in blue the indoor one. And then we have two sets of three curves. The three black curves are the central moving average and the two percentiles computed considering only night data. So only data collected in periods during which the heating was not on. So let's say that night data are a sort of indicator of the natural microclimate of the church, while the three red curves represent the moving average and the two percentiles computed on all data, so considering the entire set of data. It is clear that especially in autumn and winter, so when there is a strong use of artificial heating, there is a higher mismatch between the two sets of curves, and in particular, the effect of heating shifts these curves towards lower values of relative humidity, and so there is a different definition of the safe and risk area for the relative humidity fluctuations. So if we focus on night data, these are, as I just said, an indicator of the natural microclimate of the church. For this reason, we can define a delta RH, so a delta relative humidity, meant as difference between the relative humidity measured at the start of scheduled events, like for example Sunday services, that together with funerals are the most common and the most frequent during the calendar year, and the relative humidity coming from the moving average calculated on night data. So this value of relative humidity is something that represents the natural microclimate of the church. In this graph, you can see scatters that represents the entity of this delta RH. The graph is divided into 4 regions, one for each season, and we have these orange regions that represents the periods of time during which the heating is used. We can see that especially in autumn and in winter, so when there is a much stronger use of artificial heating, this delta RH has very low values, and it reaches a minimum of about -40%. So this means that the actual measured relative humidity has a significant distance from the moving average, so from the natural microclimate. So the effect of heating is quite strong. Now, if we want to identify the relative humidity variations due to use of heating, it is fundamental to consider the entire set of data. And so we are able to, again, using the standard, calculate the fluctuations of relative humidity and to compute the moving average and its percentiles in order to define the safe and risk area. So here you can see the 2 percentiles in the central moving average calculated considering the entire set of data. You can see how, especially in autumn and in winter, the relative humidity variations drops in particular are so significant that the relative humidity falls below the lower percentile. So the relative humidity is in the risk area, is often in the risk area when the artificial heating is used. So if we take as example a point in which the relative humidity experiences a very low drop, this point has a given distance from the moving average. So this red bar is the difference between the measured relative humidity in this point and the moving average point of relative humidity. The green bar is, on the other end, the distance between the moving average and the lower percentile, that is the lower bound of the safe area. So if the red bar is greater than the green bar, it means that the safe bound has been exceeded, and so the relative humidity falls in the risk area. Following this simple condition, it is possible to evaluate all the 10 periods in which the relative humidity crosses and exceeds the lower percentile. So we are able to identify RH start and RH minimum, intended as the first point of relative humidity that crosses the 7th percentile curve, and the the minimum of the relative humidity in this range, and we are able to identify T start and T end like the two time instants that confine this range. So we can define a relative humidity drop intended as the entity of this difference. So the difference between RH start and RH minimum, that in this case is of about 15%. From metadata, we know that on October the 12th, 2019, there was a funeral at 12 o'clock. As a matter of fact, we can see that at 12, and in particular a bit after 12. So at the end of the funeral, after the end of the funeral, the relative humidity starts to increase because the heating had been turned off. We know that the heating has been turned on way before the event. As a matter of fact, we can see how the relative humidity starts to decrease some hours before 12 o'clock. So if we want to understand the actual effect of the use of heating, we would like, for example, to calculate the entity of the entire relative humidity drop. So not only of the amount of relative humidity that goes below the 7th percentile. For this reason, we are trying to propose a possible new strategy to identifying these relative humidity drops. So if we consider a time window of length L, and so we have this data confined in this brown bar, we can compute the median of this data. Then we can define a difference in relative humidity as the difference between the relative humidity of the following value, so at I plus L, that is represented by this green bar. So the difference is between this value and the median of the L data calculated before. If this difference is negative, and if its absolute value exceeds a given threshold, it means that relative humidity is decreasing. In particular, if the relative humidity of the successive values is still lower than the median calculated before, it means that the relative humidity is still experiencing a drop until it reaches a value that is about 90% of the initial median of data, because it means that here the relative humidity has gone back to its reference state, so to the state that was experienced before the heating had been turned on. This way, we are able to identify all this entire range of relative humidity, so the entire drop. So if we compare these two strategies, we can see that following the standard, we are just able to identify the amount of humidity that exceeds the lower percentile. So we have no information about to identify the point at which relative humidity starts to decrease. While in this other case, we are able to do this, and we are able to compute the entire drop, that in this case is of 40%, because it is intended as the difference between RH start, so the point in which the relative humidity starts to decrease, and the minimum. So the main difference stands in the identification of RH start. In the first case, it stands for the 7th percentile, while in the second case, it is the point in which there is the start of relative humidity decreasing. So if we want to understand better the differences between these two strategies, we can, for example, take a look at these plots, one for Ringebu and one for Heddal Church. In these plots, we have on the x-axis the RH start defined with the proposed strategy, so intended as the point in which the relative humidity starts to decrease. While on the y-axis, we have the RH minimum, so the local minimum of relative humidity experienced during the drop. The order is reversed. Here we have these isolites that are delta RH isolites, so relative humidity drop isolites. This means that, for example, if we have an RH start of 80% and a drop of 20% is experienced, an RH minimum of 60% is reached. All these points, these scatters that you can see here for the two churches, are all the relative humidity drops that have been detected with the proposed strategy. The color of each scatter depends on this color bar. This color bar represents the difference between the two strategies. So the difference between the starting point used for the two strategies. So RH decrease minus the 7th percentile. It is clear that when RH start has high values, the error, so the difference between the two strategies, is higher, because the starting values of relative humidity is far away from the 7th percentile. So it's nearer the higher percentile, the 93rd one. For this reason, this case, using just the European standard leads to higher errors. In addition, experimental during some experimental campaigns and some experimental tests, a relation between the relative humidity drop and the agromechanical stress in Scots pine wood was found. So here we can see the same graphs as before. So the meaning is the same of the two axes and of the scatters, but here now we have these contours, so these bands, these colored bands that represent the experienced agromechanical stress, whose identity is represented by these color bar. It was experimentally found that in general, failure happens if relative humidity drop of at least 35% is experienced. So one would be led to describe the failure areas as these two gray triangles. So considering the isoline of delta H equal to 35% and going from this line on. Anyway, if we take a look at these colored bands that represent isostress bands, we are able to plot these isostress lines. And as it has been experimentally seen that failure happens if a stress of at least 9 megapascals is experienced, and the plastic deformation happens if a stress of 3 megapascals is exceeded, we could think to describe and to draw new failure and deformation areas. For example, if we follow these isolines of stress, you're able to identify the failure area, that is the gray one, and the plastic deformation area, that is the yellow one. We can see that in this case, the areas are like wedges. So the narrow part of the wedge is towards low values of RH star. This means that even low values of RH star could be damaging because it is fundamental to be careful to not exceed the plastic deformation area and go to the failure area. So underestimating or misestimating the RH drop could lead to a bad estimation of the experienced agromechanical stress. This could be risky for the conservation of wooden objects and artifacts. So concluding, two Norwegian stave churches have been analyzed, focusing on the mixed microclimates and using their metadata. The European standard has been fundamental to estimate the relative humidity variations caused by the use of heating, and most of them lay in the risk band of relative humidity. New approach has been proposed, and it has been seen that if relative humidity has values near the higher percentile, the misestimation, so the difference between the two strategies, is higher. There is a relation between the relative humidity variations and the agromechanical stress, and even low starting levels of relative humidity could be damaging. So the European standard is fundamental for specifying the relative humidity fluctuations because they cause irreversible physical change of organic hygroscopic materials, but the standard alone may lead to the neglection or underestimation of some relative humidity fluctuations, which are significant even if still in the safe area. So in this framework, what could or could not be done for the stave churches management in the framework of the cultural heritage conservation? First of all, the sporadic uncontrolled heating is not recommendable, while continuous heating is preferred. As a matter of fact, it has been seen that, for example, in Ringebu Church on November 2019, it happened that the heating had been kept on for 5 days continuously. So this is quite worrying, because during this very long period, wooden objects could have acclimatized to this new condition, to this new microclimate condition, and then at the end, they are forced to go back to the previous condition. And this could lead to the formation of internal stress fields and possibly to failure. For this reason, sporadic heating is recommended if it is regulated with a timer and temperature controller. It is not recommendable to turn the heating on too many hours before scheduled event in order to avoid the high temperature difference between indoor and outdoor, even to avoid that the indoor temperature is too high, so to avoid the over dryness of the indoor environment. It is okay to allow visitors in non-heated periods, so in the warm season, in order to avoid to further turn on heating in the cold season. Take note of metadata is fundamental because it is useful to understand the use of the churches and all the events and number of people that take part of those events, and monitoring the temperature and relative humidity with data loggers that are very simple and cheap sensors is useful to to keep an eye on the temperature relative humidity profiles for cultural heritage conservation purposes. So concluding, a couple of simple tricks could be surely life-saving for the preservation of historical buildings and money-saving for the buildings management. With this, I conclude. I really thank you for your kind attention, and I look forward to meet you at the Symbol Conference.